All right, let's get started. Physics test, so our numbers are probably even more limited than normally. A couple logistic things about the trust checkouts. All right, I share an office with 5 graduate students. Okay, you don't get the nice office until they give you the nice degree. Only one of those graduate students knows anything about statics, and that's Stu. Okay, so when you're coming in to check out your trust sets, please be respectful of them. They're doing their own work. They don't know anything about they know I'm teaching statics. They know we have office hours, that's why we have them down the hall. Okay, don't bring a trust set to them and ask them to check it in. They don't know what that is. And also be respectful of the time of your checkouts. Okay, those are specific. Okay, I'm not always in my office. Yesterday, I work off campus on Thursdays. So the checkout at 5 and the check-in at 4:30. Just please be respectful of that, because that's when we are planning and committing to have somebody at my desk for you to check it in or check it out. Okay, does that make sense? So we have folks checking it in this evening at 4:30. Okay, and another group checking it out at 5. Okay, so please be respectful of those times. Okay, it's Friday. I'm not going to sit around until 6:30 tonight waiting for you to come. So if you're not there by 5:30, 5:15, okay, it's up to you to be responsible to be on time. All right? Any other questions? Are your trust designs going well? Any questions on the pre-lab? Who's going to win the competition? Everybody? We've got 3 groups. I don't know, Bobo has some work to do with their Hobbit house that he built. Don't build squared. Remember, these are trusses. We're not building squares, and we're connected at the joints. I think he had some like duct tape in there at some point. All right? So, if we're good on the lab, okay, I'm going to send out a reminder email this weekend about logistics. We're not going to be in CMK, but just be looking for that this weekend. Today we begin our 4th and final module. Okay, I know you're sad. Okay, I was actually expecting some tears. Okay, but this lecture will not be on our quiz on Monday. Okay, quiz 3, exam 3 is just our module 3, our structure module. So trusses, frames, and machines. Okay, it's short. There's only 4 lectures in that module. And remember that I started filming them. So all of the lecture videos with audio and the board are posted on Canvas, okay, under the Pages tab. So as you're studying, if you find that those will be useful, those are for your disposal. Has anybody even tried to find them? Excellent. I thought like all the 12 views was me trying to figure out how to upload it. Okay, so they're up there, they're right in Canvas. Okay, use those if you're confused about anything as you're studying. All right, so today we begin again, we keep adding to our realistic mechanics analysis. Okay, so up until this point, we have been making an enormous assumption in our mechanical systems. Okay, so if you printed out the notes or you're looking at the slides, what is that assumption? No friction. We have assumed up until this point that all of our surfaces are frictionless. Okay, and in reality, there is no frictionless surface. Okay, as a plug, if any of you design or invent a frictionless surface, you will be incredibly rich. And if you can just give me a little bit of that money, I will appreciate it. All right? So in mechanics, we have 2 types of friction. Okay, what is friction? You've seen it in high school. You've probably seen it derived in physics. But what does it mean? The friction between us after you get a test back? Okay, yeah, sure.
Forces resist motion in the object that is contacting it.
Perfect. So Asher says it's the force that is resisting motion between 2 surfaces. Okay, so in mechanics, there are 2 types of friction. There's dry friction, and we will also call it Coulomb friction. Okay, Coulomb was like a 16th century physicist that derived a bunch of very impressive things. And we also have fluid friction. All right. So in this class, we will focus on dry friction. Okay. Fluid friction, you have contact between different types of fluid. That is something that you will have with Dr. Roselle, possibly Dr. Gordon, Dr. Langsfeld, all of those fluids folks. But for the sake of this class, we only have dry friction. Okay, so again, to reiterate what Asher said, that dry friction is the force that is resisting motion between two surfaces. Okay? So within Coulomb friction, within this dry friction, we have two types of friction. Okay? We have static friction and we have kinetic friction. Okay, so this is within your mechanics, within your statics and dynamics. You have static friction and kinetic friction. Okay, in this class, what are we going to be focusing on? Static. Excellent job. Okay, static friction, nothing is moving. Okay, and kinetic friction is the force between two surfaces when in motion. All right, so let's consider this classic example of a block on a surface. Okay, you probably saw this in high school, saw it in physics. We have a block with a weight W acting through its center of mass. Okay, it's on a surface. Okay, it's on a surface, and we are applying a known force P. Okay, what other forces are acting upon this block? We have a normal force. Okay, we have a constraint force that is holding the block on the surface. Okay, there's a force from the table on your block, from the ground on your block. Okay, that's a constraint force. Okay, and now we have a friction force. Okay, which we will indicate with F. All right. So in this class, we know that F, our friction force, the force that is actually opposing your motion, is equivalent to mu S times N. Okay, this N you probably are familiar with. It's the normal force. Okay, typically that's equal and opposite to the weight. Okay, but not always, and we are conveniently going to do an example where that's not the case. Okay, but this mu S, have you guys seen that before? What is it? The coefficient of static friction. Okay, in physics you may have been given it all the time. Okay, in this class, not the case. Okay, we can derive it using our equilibrium equations. Okay, we can solve for that ratio. All right, and we also have mu K, and that's the coefficient of the kinetic friction. Okay, not as big of a deal in this class. Okay, so your force, your friction force that's opposing your motion, is a function of that coefficient of friction, coefficient of static friction. Okay, that's a property of the two materials, and the normal force. Okay. So if we have this classic example of a block with a force applied, okay, as we increase P, what happens to that friction force? It increases, right? In statics, as you increase a force applied to an object, the friction force resisting that motion, that force, has to increase linearly, right? It has to increase linearly in order to maintain equilibrium. There is a point, however, when that friction force, that force P, exceeds your allowable friction force, and we get into the land of kinetic friction. So there is this threshold. Okay, there is this threshold. We have Fs, okay, the static friction force increases linearly as a function of P. Okay, the larger the force P is, the greater your static friction force has to be to maintain equilibrium. Okay, once that force P is exceeded, okay, we get into motion. Okay, and most often, almost always, mu S is greater than mu K. Your coefficient of static friction is greater than your coefficient of kinetic friction. Why is that? If it's the same material. Yeah, Asher?
When objects are still, the microscopic imperfections on their exterior tend to settle into each other, whereas when they're moving, the materials tend to kind of slide over each other instead of their grooves
Okay.
sitting in one another.
I'm sure you're right. I'm not a materials person, but I know Dr. Camosa and Dr. Laz are probably wishing they were here to recruit you. So Asher may have a materials future ahead of him. But in terms of Newton's laws, okay, an object in motion stays in motion. But to get it in motion, that force is larger. And I'm almost positive that it's because of what Asher says, is that contact between those discontinuities of the surface. Okay, to overcome that discontinuities requires a greater amount of force. All right? So today we're going to, it's structured a little bit differently. Okay, I'm just introduced friction. I want to jump right into an example. Okay, right into an example, and then we're going to come back to the concepts behind friction once we've seen it applied. All right? So you all have probably seen the example of a block on an inclined plane. You've seen it in physics, seen it in high school. Okay, you solve for the friction force and you're done, right? But we're engineers, we're going to apply it. We need to know what that means. Okay, so in this example, we have a block on an inclined plane that is attached to a pulley. So this is a machine, right, where we have an inclined plane and a pulley. So what are the constraints? Partially constrained, fully constrained? Is there a degree of freedom? It's partially constrained. It's a machine. There is a degree of freedom that allows this block to slide up the plane. Okay? That doesn't affect our friction analysis, okay, but it is important to know that in statics, even though this block may be sliding up the plane, we are solving it at an instantaneous point in time. So if we want to solve for this friction force, okay, if we apply a 400 Newton force in the cord, how would you do that? How would you start it? Free body diagram. Okay. And I also want to jump on, today's going to be a little different, is I want everybody to get out their calculators. Okay. So while I draw this free body diagram, get out your free body diagram. Get out your calculators. Okay. On this free body diagram, okay, we have a known weight of 800 newtons. Okay. We also have a known tension in the cord of 400 newtons. What don't we know? What don't we know, Nick? Remember, a free body diagram has known and unknown forces. We have a normal force. How would you draw that? So Nick says there's an x and y component of the normal force. In other words, what I'm interpreting from that is the normal force is perpendicular to the surface. Okay, excellent. So we have a normal force that is perpendicular to the surface, that is restricting motion. Okay, it is restricting the block from falling into the surface. What else don't we know? Friction. Okay. So we have a friction force F. Does it matter what direction I draw these? No, with an asterisk. Okay, in statics, it does not matter. When we apply our equations of equilibrium with our sign convention, okay, the math will tell us if we've drawn it correctly. That changes in dynamics. So in the spring, when you're solving your equations of motion and friction's in there, okay, there is some intuition that you need to apply. That's a whole nother concept. We're not going to get into that, but I just wanted to forewarn you. So when you walk in after spring break, you're not totally freaked out. So in statics, Doesn't matter. All right? Can we solve this yet? Who says yes? Keenan says yes. Asher and Nicole. Everybody else is still watching the Broncos game. What do we need? What are we missing on a free body diagram? Say it. Sign convention. In dimensions. So the sign convention, okay? A rule of thumb with these inclined plane problems is to put your coordinate system parallel to the plane. Okay? That, again, will make your life tremendously easier in dynamics. In statics, in this problem, it really doesn't affect much. Okay? We would have to decompose two forces regardless of if we tilt our coordinate system parallel to the plane or if we keep it directly vertical and horizontal. Okay? This is still a right-handed coordinate system. Okay? It does not matter how we orient it. Okay? But this makes your life easier in dynamics, and so I want you to get in the habit in statics of rotating your coordinate system to your advantage. Okay? And then what I think Curtis said was we need dimensions, and we were given that this block is oriented with respect to the horizontal at 20 degrees. So now, can we solve this? Okay? How would you solve it? What are we solving for? Some of the forces, some of the moments, that's always a good answer in statics. But what are we solving for? This friction force F. All right? So if we sum the forces, which component would you use? We have X and Y. We have X. Let's use X. Okay? We've rotated our coordinate system to be parallel with F. So we've immediately negated our normal force. And that's an advantage of rotating our coordinate system. If we had our traditional Cartesian coordinate system with Y vertical and X horizontal, you would have a friction force and a normal force, two unknowns in each equation, and you would have to solve a system of series of equations. Okay, so another trick, there's nothing wrong with that. Nothing wrong with that. Okay, but we know that as engineers we are lazy. Okay, let's take out that unknown. So if we sum the forces in the X, what does that look like? What's in that equation? Carson? F? Plus 400 cosine 20 minus 800 sine of 20. Excellent. So in your calculators, somebody solve F for me. And I will give you a prestigious prize of a warhead that was found on the table. Now you're punching. Okay. I want to get you guys in the habit of solving these. Right? Solving these equations. Don't take it for granted. Negative 102.3, I heard it. Nice job, Mike. So we have our friction force. It's negative 102.3 newtons. Okay, so what does that mean? Stay with me, guys. What does that mean? It means it's in the other direction. This friction force, okay, is resisting the upward force. So it's not always in the direction of motion, okay? It's resisting that upward force. All right? Do we know if the block is moving? Who says the block's moving? Nicole says the block's moving. Bobo says maybe. Drew? Drew thinks it's moving. Who doesn't think it's moving? He thinks it's statics. Well, nothing's moving. Who doesn't know? Who thinks we could maybe figure that out? Okay. So yes, it's statics. Things aren't moving. But recall with machines, with these partially constrained machines, Okay? They are moving, but we are solving them at an instantaneous point of time, right? Statics is just your foundation of mechanics. We're building our way up, okay? But there's nothing in this problem that tells us if we are moving. Okay? Nothing tells us where we are on this curve in looking at that problem. Okay? How would we figure that out? We're given the, so Mike says find the coefficient of friction, but we're given it in the problem. Asher? Solve for the resultant force. What do you mean by that? Say that again.
If there's some force acting on it that's greater than the static friction opposing it will move.
If there is some force that's greater than this static friction force, F max, okay, it is the function of your coefficient of static friction and your normal force. If the resultant force, okay, which I think that language is right, but our result, yeah, I would agree with that. Our resultant force, if it's greater than F max, we are going to be moving. Okay, if we fall somewhere on this curve, we don't have enough force to overcome the friction, and so we are stationary. All right? So to solve for that, to solve for what that maximum force is, what do we need? The normal force. All right? How do we solve for the normal force? Some of the forces in the y. Okay, so what's in that equation? N? What's that? 800 cosine? 800 cosine 20. Is that positive or negative? Negative. Okay, we're pointing down. Even though we're oriented at an oblique angle, we're acting in the negative y direction. So negative 800 cosine 20. Okay, what else is in there? 400 sine 20. Okay, I heard plus and minus. Who votes positive? Front row. Who votes negative? The back row. Okay. Why is it negative? Exactly, okay. If we look at our coordinate system, it's still pointed. There's our y, there's our x. Okay, our force that we're applying, okay, this is exaggerated. We are still in the negative y. So negative sine 20. And I already heard it. Wait, yeah. I already heard it. N equals 888.6 newtons. You ready? Peyton Manning it. All right. So our normal force is almost 890 newtons. All right. So we can solve for this maximum force, which is a function of your coefficient of static friction, which we are given. Stay with me, guys. Coefficient of static friction times that normal force. 888.6. We solve for the maximum force to be what? What is it, Bobo?
Sorry, I'm insulting Jack.
You were not consulting Jack, okay? If you want to insult him, do it outside. 355.4. Okay, solving for this maximum force in this loading condition. Okay, this F max is 355 newtons. Are we moving? I heard it. Who said it? Why? Because our friction force is 100. Okay, we are somewhere down here. So we're in the region of equilibrium. We will call this the region of equilibrium, statics land. Okay, we have not exceeded the maximum allowable force, okay, as a function of our coefficient of static friction and our normal force. Yeah, Nick?
What is that value? That's friction in that direction.
What is what value F?
The value of
Negative 102? What is, so Nick is asking, what is this F? What is this? Force of friction, but what does that mean? Carson?
What's the force of friction assuming that it's in static equilibrium? So if that was greater, then wouldn't it be moving? Because that's not possible if it was greater than.
Close, but remember it's statics. So Carson said, so say that again?
I heard it's the force to keep it in equilibrium.
So it's the force to keep it in equilibrium. Okay, but we were just given a loading condition. Okay, it just so happens that we are in equilibrium. Okay, but what does that mean in your own words, Jack?
So that's the force of friction being applied to the block, but when we get there, we don't know if that is static or kinetic friction. So then we have to sort of solve for the, as you called it, the friction threshold.
Mm-hmm.
And if we are below that, then we know that that force of friction is due to static friction.
Mm-hmm.
Conclude that we're not.
That's absolutely correct, but I don't think that's what Nick's asking.
No, that's what I was.
That's what you were asking? Okay, so we don't know. Okay, we get 100 newtons. What that's saying is that as we apply a 400 Newton force in this loading condition, it is resisting the motion with a magnitude of a force of 100 newtons. Okay, and that's fantastic. Okay, and that's probably where high school stops and where physics stops. Okay, but as engineers, we need to know what's going on in the system. Yeah, Bobo?
I'm confused for the graph over there.
Mhm.
Because F is less than F max, like how do we know if it's moving? Because you see how it goes up and then goes down. What?
So Bobo asks, on this graph, what's going on? How do we know if it's moving?
Because like 102 is less than F max, but also the force to move it is also less than F max.
The force to move, how do we know the force to move it?
It drops down.
Okay, so that's when you're in this kind of interesting discontinuity. Okay, this interesting discontinuity of this complex material that's dependent on your material properties. Okay, but this region is exaggerated. Okay, it's really not that large. Okay, but that also is a function of your P. Okay, if you apply, okay, a huge P, okay, and you get some force, some kinetic friction force down here, where are you on this curve, on the side? Down here, right? It's just an XY plot. Okay? So I think part B might help clear up what this graph is telling us. Okay? But does that make sense, Nick? Okay. Are you with me, Bobo? Kinda? Okay. I'm going to come back to you after part B. Okay. So this part B asks, find the largest allowable tension, okay, that will not move the block. Okay. So we were solving for this largest allowable tension that will move the block. Okay, anything less than or equal to this tension, we will stay in equilibrium land. Yeah, Bobo?
Wouldn't you just sub in the force of friction with F max?
Who thinks we've already solved? We've pretty much already solved for F max. Plug it in and solve for solve for tension. We have one vote down here. Keenan. Curtis says we have a vote. Jack says maybe, but he's questioning it as I continue to ask questions. Why can't I do that? Carson?
Because when we solve for n, we use that 400 newtons, and that 400 newtons is the variable.
Excellent. as we solved for our normal force, okay, we inserted 400 newtons. Okay, this normal force, okay, the normal force is a function of this tension, and that's because they share rectangular components. So yes, Bobo, in some cases, our maximum force, okay, if this had been an even surface, is constant. But in our loading conditions, with this normal force, it's a function of tension. So how do we overcome that? So how many unknowns do we have now? We have two unknowns. What are they? We have our normal force and T max, okay, which are coupled together. Are we out of luck? Nope. Why?
We haven't used moments yet. Could use moments for this? Or?
I don't think you're on the right track. Keenan asked if we could find the moments. Okay, doesn't totally apply here. But in statics, we have our equilibrium equations. How many of those do we have? We have two. Are there any green light bulbs going off? Ding, ding, ding. Two equations. How many unknowns? Two. Okay. So if we sum the forces in the x, okay, our equation, we already have it on our paper, right? We have negative 800 sine 20 minus our friction force. Recall that we found that it is actually opposing motion along the inclined plane. Okay. But I'm going to put 0.4 times n. Okay. We are solving for this normal force that will equal our maximum allowable threshold of friction force. Okay. So this 0.4 times n is our friction force. Okay. Sum of the forces in the x, and we also have a plus T max now. Recall in part A, that tension was 400 newtons. So T max times the cosine of 20 equals 0. I have another equation in the y, correct? Fy equals 0. Okay. We also have already solved for that to be negative 800 cosine 20 plus n plus our normal force, okay, minus T max sine of 20 equals 0. So who can solve for this? Who's working on it? Who's maybe using a helpful linear algebra trick that was maybe suggested earlier to solve for it quickly? Okay, we have two unknowns. We have two equations and two unknowns. Okay. I want you to be able to solve for this because this is completely fair game for any homework or exam or final. Okay, you need to be able to solve for two equations and two unknowns efficiently. Asher, do you have a calculator?
I forgot.
You got to warm up for your physics test. I see calculators out and people staring at me. Okay, we need to know these both because our normal force is a function of the tension. Who's solving this the long way? Okay. So for time's sake, make sure you can solve this system of equations, okay? Because when writing exams, I'm not going to count in 10 minutes for you to solve this. Okay? So make sure you check your answers later. You get your normal force to be 996 newtons, and your maximum tension be 715.3 newtons. Okay? So when the force in this cord is 715 newtons, okay, we will move into kinetic friction land. Yeah, Will?
What's the linear algebra or something?
Come to office hours. Okay, I'm running low on time. Okay, but that is fair game. All right. So for the sake of time, because we have a guest speaker that I'm going to turn it over to in a few minutes. Okay, we have another example. Okay, that is a little more conceptually driven. You guys have seen this math. Okay, I know you're fine with this math, or you need to be. Okay, I want to talk about this curve. Okay, I want to talk about what this curve means. Okay. So in mechanics, okay, and in your reading last night, I hope this might sound familiar, is that we kind of have 4 scenarios that occur in these friction problems, in real life problems. Okay, and I want to introduce some new words that you may or may not have heard, okay, these concept words. Okay. So we kind of have these 4 loading conditions. And in mechanics, the first is we can have a force applied to a body that is so infinitely small, okay, that it is essentially zero in respect to its structure, that it will never cause motion. Okay. And a real-world example of that would be like a wind force on a skyscraper. Okay. Those structures are built so that force applied, that wind force, that continuous distributed load across the surface of the building is so small it will never cause motion. Okay. But we also have, okay, a loading condition, which we just looked at this last example, okay, that was somewhere on this curve, that was in this equilibrium land. And it wasn't causing motion. And that's what we will call not impending. Okay, so on the left-hand side, okay, in this class, I commit to you that we will stay less than or equal to the left-hand side. Okay, our motion is not impending, but those loading conditions could potentially cause motion. And that's when we come up to the peak of this force. Okay, so that second condition is it's not impending motion. Okay, the applied forces have the potential to move the body, but they're not large enough to set the body in motion. Okay. The third condition, okay, is what we will call impending motion. The applied forces are about to set the body in motion. Okay, so this F max, this threshold, we will call impending. Okay. Those, as Asher said at the beginning of the class, those material properties are just coming apart and we're about to be in motion. And then we get to our fourth case, in which the body is in motion and we now have to take into account kinetic friction. And that's what you will work with in the spring with Dr. Davidson in dynamics. Okay? So not impending motion, we are in the land of equilibrium. So we can apply our equilibrium equations. Okay, not impending motion, we apply our equilibrium equations. To determine when motion is impending, that's when we can solve for that threshold. That maximum force is a function of the normal force and the coefficient of static friction. Okay, so I will post, I have a few notes that I'm going to post, a problem and a few comments. So look at that. It's not going to be on the test on Monday. So now we have a guest speaker, Dr. I forgot your name. Dr. Bavlo? Balzor. Okay, he's going to, okay, sorry.
This is probably more appropriate.
Yeah.
So I know you got a physics test coming up. I also know a few of you expressed